Okay. So yes, I'm going to present a work I've been doing at the University of Luxembourg with Massimiliano Esposito, where we studied the thermodynamics of the coherent energy exchanges between lasers and atoms. So so this is a theoretical work. The model we study is this simple model that Benjamin Howard talked about on Monday. So you have an atom modeled as a two-level system or a qubit, which is on the one hand driven by an external laser beam, which induces a coherent driving. And it's also coupled to a cavity with which you have spontaneous emission processes which act as damping. So this process is in fact extremely, as you know, very broadly used in the context of nanotechnologies for the implementation and control of quantum gates, for example, and also in quantum simulation. And in all of these applications, it's often very useful to have a master equation in order to study the reduced dynamics of the atom. Now, this problem is also textbook in quantum optics, and you have, to describe the atom's dynamics, the Bloch and the Floquet master equations, where the Floquet master equation stands in the very strong coupling regime. So what is the question we want to address? So because of the widespread use of this process in nanotechnologies, there's been an increasing interest questioning the thermodynamic consistency of these two equations. So what do I mean? So thermodynamic consistency is a concept that comes from stochastic thermodynamics, which tells you that any thermodynamic quantity that you compute from the stochastic dynamics, meaning from the master equation, should have a thermodynamic interpretation at the microscopic scale. Now, this question has been addressed for the Bloch and Floquet master equation, specifically in those recent works here by Cyril Elouard and Alexia Ofev and Massimiliano Esposito and others, where they found that the Bloch master equation is in fact consistent on average, meaning that it does maintain the first and second laws of thermodynamics. You've also had works on the Floquet master equation in the steady state regime. But what we want to address here is to try to go a bit further and question, can we say something about the consistency at the fluctuating level? Meaning, do these equations also satisfy fluctuation theorems? And can we say something about the energetics at the fluctuating level? So to address this question, the strategy is the following. We will first study the unitary case and identify laws of thermodynamics, identities, and the fluctuation theorem that hold at the unitary level. Then we derive master equations and examine whether they preserve those symmetries that hold at the unitary level. So the fact that we have a time dependence here in the Hamiltonian makes the study complicated. So to avoid the complications, we move to an autonomous description. So to do so, we basically extend the Hilbert space. Instead of having the laser described as an external drive, we describe it as a coherent mode on its own, described by a time-independent Hamiltonian HL. So now the total Hamiltonian of the system is you have the one from the atom, the one from the environment, so that cavity, the coupling between the atom and environment, and then you have the Hamiltonian of the laser and the coupling between the laser and the atom. So let's focus first on the system consisting of the atom and laser. Because it is convenient to study this system in what is called the dressed atom picture. So in the joint basis of the atom and of the Fock basis of the laser, the two processes I talked about earlier, the stimulated emission, so this is the drive from the laser, and the spontaneous emission, are modeled by these transitions here. So basically, during a stimulated emission or absorption, a photon is absorbed from the laser drive by the atom that goes from the ground state to the excited state. In a spontaneous emission, on the other hand, the atom goes from the excited state to the ground state, and the number of photons in the laser stays constant. Obviously, the Hamiltonian of the laser and atom is not diagonal in that basis because of the interaction. So you can go to the eigenbasis, which is called the dressed basis. In this new basis, labeled by those 1 ends, 2 ends, the spontaneous emission now couples all of these states, and you have three emission frequencies in the emission spectrum equal to omega L, the frequency of the laser, and then omega L plus or minus omega, where omega is the Rabi frequency. Now, the point is that when the laser is in a macroscopic coherent state, the interaction here simplifies. You can basically assume that its amplitude is constant, and then you have a mapping to a new Hilbert space. Like you can decompose this initial Hilbert space of the atom and laser to a new product of Hilbert spaces of the dressed atom and dressed laser. Simply by this formal mapping here, but essentially what we're doing is a change of basis in which the Hamiltonian is not diagonal and can consist of two terms. You have a two-level, the Hamiltonian of a two-level system of energy omega, and that's the dressed dressed atom, where the omega, the Rabi frequency, depends on the strength of the coupling. And then you have the Hamiltonian of an infinitely leveled system, which is, by symmetry, we call it the dressed laser. It's basically the initial laser slightly modified by the presence of the atom, but which is also still in a coherent state. So the relation between the Hamiltonian of that dressed laser to the initial one is they're related by this identity here. Okay, so now I will discuss in this basis, discuss the laws of thermodynamics first at the average level, and then we'll move on to fluctuations. So the standard approach in quantum thermodynamics, when you have a system coupled to some thermal bath, and with possibly a time-dependent Hamiltonian, you define the heat as the variation of the energies from the environment or that bath. The work is instead given by the time variations of the Hamiltonian. And then energy conservation tells you that if you define the energy of the system as the energy of the Hamiltonian plus of the interaction, you have the first law of thermodynamics. If now the initial system is factorized between the system coupled to a state at equilibrium, you can obtain the second law by this identity where this D is a relative entropy, so which is positive. Okay, so we will use, let's say, these definitions to derive our laws of thermodynamics. So here, the Hamiltonian is completely time independent, so you don't have the work in the sense that I defined in the previous slide. I also mentioned just one point here. In what follows, we will always assume that the interaction with this thermal environment is weak. So we basically can neglect it, and to alleviate the notation, I will not write it explicitly there anymore. Okay. So using these definitions, we can now do energy balances in the we can do it in both pictures. Either we're interested in the non-dressed basis, so studying the atom itself, or in the dressed basis. In both cases, the heat is always defined as the variations of this environment here, the thermal environment. In the first picture, basically the idea is to consider this environment here and the laser as two reservoirs that the atom is coupled to. So we introduce the energy variations of this laser this way. And if we define the energy of the atom as the Hamiltonian of the atom plus its interaction with the laser, you have a first energy balance there. In the dressed atom picture, there is no more interaction between the dressed laser and dressed atom, so you can just define the energy of the dressed atom by the variations of the Hamiltonian of the dressed atom, and you have another energy balance. Now the point is that those coherent states, either the laser or the dressed laser, can be considered as work sources, even if defined by time-independent Hamiltonians, because they exchange energy and no entropy with the system. So here we use a notion of work source coming from a resource theory, and you can find details in that reference here. And so because of this, we identify the energy variations in that dressed laser or the laser as work sources, and then you have two expressions of the first law. The quantities in those first laws are related by those identities, which come from the fact that the Hamiltonian of the laser is decomposed as the one of the dressed laser plus that term here, omega over 2 sigma z, that I mentioned earlier. So this is for the first law. I will now just quickly mention the second law. So essentially, everything also works very nicely if we just assume that the initial density matrices is factorized. Again, you can do that either in the dressed basis or in the normal basis, and you have these two identities here. Since the laser and dressed lasers are coherent states, you can neglect their entropy variations, and you have, again, your first laws. Now, so this is all in the this time-independent picture. I briefly mentioned that you actually can recover and do the same analysis even in the time-dependent case, just using the fact that you can move back to a time-dependent description using a unitary transformation called a Molo transformation. So if you look at the density matrix rho tilde, which is defined from the initial density matrix by applying that unitary, where D is a displacement operator, which basically acting on the vacuum can create a coherent state. Then you map your initial problem to a problem which is time-dependent with a Hamiltonian that is periodic. Since it's only a unitary transformation, the energy of the atom in that tilted picture, in that time-dependent picture, is the same as the initial one. And you can check that, in fact, even if you start from the usual definition of energy that you would have with time-dependent Hamiltonians, you recover that everything works neatly with a first law, which is written in this form, where the work here is given by the time-dependent part of the Hamiltonian, but you can check that it's identical to what you obtain in the autonomous picture. The connection with the dressed atom is simply to notice that in the rotating frame, the dynamics and thermodynamics is identical to what happens in the dressed atom basis. Okay, so now we did everything at the average level, and now let's move on to the fluctuations. So to study fluctuations, I'm going to use a method that was presented in a talk yesterday by Hassan Nazir, which is basically two-point measurement techniques with counting fields. So when you have an observable that depends on time, you can measure a fluctuation of that observable using a two-point measurement. So you measure it at time 0, at time t. The statistics of the outcomes of that measurement is given by the probability delta A to observe a certain outcome. And in order to fully characterize the statistics, you can compute the moment generating function, which is the Fourier transform of that probability distribution. What is interesting is that this moment generating function is also equal to the trace of a density matrix dressed with counting fields, this rho lambda, where rho lambda is the solution of that unitary evolution, where the propagator is the initial propagator dressed with the counting fields of whatever we are counting. So the only thing to remember from that slide is that to perform analysis of the fluctuations, we want to compute this moment generating function, which is that trace of that rho lambda. So in the present case, we want to study the variations of the energy of the dressed atom and the lasers and etc. Because all of these Hamiltonians commute, we can measure them simultaneously and define a joint generating function with each of the counting fields corresponding to counting these different quantities. And what we found is that you can express a fluctuation theorem as a symmetry of that moment generating function. So the theorem is the following: if you have initially your density matrices which are fully factorized, both for the forward dynamics and for the time reverse dynamics, then the moment generating function of the forward dynamics is related to that of the reverse dynamics by that symmetry. So it might not be very intuitive to see how this connects to fluctuation theorem. It's easier when you go back to when you perform the reverse Fourier transform. I will show that in a second. At this point, I just want to mention that basically what this symmetry tells us is that you need to apply a shift on the counting fields, which is different whether you have for the environment or the lasers. So for the thermal cavity, the shift you should apply is beta, beta is the reverse temperature. And this simply is due to the fact that the cavity behaves as a heat source. On the other hand, for the lasers, the shift is 0. And this is directly telling us that, this comes from the fact that actually the laser behaves as a work source in the sense that it does not exchange any entropy. What this fluctuation theorem also tells us is that it allows to recover the first law at the level of the rates. And another symmetry which is important in terms of, another symmetry another property that is important, which is energy conservation, can be expressed as well in terms of symmetries of this rho lambda. So maybe the formal definition is not very important. This is just a way to say, if we want that there is that any fluctuation of the environment and of the laser corresponds to a fluctuation of energy in the atom, this is the symmetry we want. And assuming that we have this strict energy conservation, from that fluctuation theorem, you can recover the Crookes law. So, for instance, if you assume that you have only one temperature in the problem, the probability then of the work given by the dressed laser is defined as the Fourier transform of that generating function. And using this and this, you recover this Crookes fluctuation theorem. Okay, but the main point of deriving that fluctuation theorem is to use that as a criteria of consistency for master equations. So now we move on to the second. We will move on to the second part of the talk, and I will distinguish between two notions of consistency. I will call thermodynamic consistency of the master equation the fact that the master equation preserves the first and second laws, whereas full consistency means that on top of preserving the first and second law, it should also satisfy fluctuation theorem and this strict energy conservation. Okay, so how do we do? So the idea is to trace out progressively the degrees of freedom that we are not interested in. So we will assume that the initial density matrix is factorized with, on the one hand, the density matrix of the atom and laser, factorized with the density matrix of the environment, and we assume that the environment is at thermal equilibrium. This allows to trace the environment and to obtain, and to keep track of the fluctuations, we do all this procedure of deriving master equations from the tilted dynamics rho lambda. So there should have been a lambda up there. Okay, so tracing out the environment, we find that the density matrix of the atom and laser is given by a quantum map M. This is standard, and then we can perform the Born-Markov approximation to derive a master equation for the density matrix of the atom and laser by taking a differential here. So the coarse graining time delta zero is submitted to some conditions that I will talk about in a minute. But already this first master equation here introduces a dissipation rate, gamma max. So basically now the timescales of the problem are, on the one hand, you have the relaxation time of the environment, the relaxation time of the atom and laser system, which is given by this gamma, and the coarse graining time for the master equation should satisfy these inequalities. It has to be larger than the relaxation time of the environment, but smaller than the evolution of the system. Now the point is to trace out the degrees of freedom of the dressed laser, and to do so we need to see how that delta zero can compare with the time scales present in the system dynamics of these frequencies. In fact, you have two regimes that are relevant and which have been discussed in this paper by Cyril and Alexia. On the one hand, you have a strong coupling limit, so which is defined by this inequality here. Remember that the Rabi frequency depends on the coupling strength. Now, if all of these frequencies here are much larger than this dissipation, then you can find a coarse graining time delta zero that can resolve all of the frequencies of the system. This means that you can derive a master equation using the secular approximation in the dressed atom bases. What we found in our previous work is that if you perform the secular approximation, you basically obtain a fully consistent master equation that satisfies the laws of thermodynamics, fluctuation theorems, energy conservation, and etc. The master equation that you obtain in that regime is exactly the Floquet master equation. So basically what we found is that that equation is fully consistent. On the other hand, if the coupling is not so strong, you're forced to choose a delta zero that is in between those frequencies and cannot really see, let's say, the Rabi oscillations. That forces you to do different approximations, which lead to the block master equation. And the consequence of these approximations is that you obtain a master equation that does not satisfy fluctuation theorems. Yeah, okay. So I just, in a nutshell, mentioned something about non-conservative forces. So from an interesting fact is that from the Floquet master equation, you can compute the work that comes from the dressed laser and find that it has this expression, and basically it involves the dissipation rates in the master equation. This is the signature of a non-conservative force. And the origin of that force is the following, that you can understand it in terms of local detail balance. Those rates in the master equation satisfy local detail balance. At the level of the atom and laser description, this local detail balance tells us that the rates of the equations are related to the energy changes between the eigenstates of the system, which means that the dynamics is detail balance. But when we are at the level of the dressed atom, instead, you have on top of this energy omega, this term omega L, that tells us that there is a non-conservative force acting. So in that case, the dynamics is not detail balance anymore, and you go to a non-equilibrium steady state. Okay, so I reached the conclusion. So I summed up all the conclusions from the work, but I put in blue the conclusions which I think are more relevant to the topic of that workshop. What we found is that basically, in the context of these periodically driven master equations, the Floquet master equation allows to compute the full statistics of the dressed laser, and that we also found that there exists a fluctuation theorem relating the fluctuations of energies between the dressed laser, dressed atom, and the heat, so the spontaneous emission, which is preserved by the Floquet-Master equation. As future perspectives, it would be interesting to study the emergence of that non-conservative force, which, yes, something I forgot to mention, that the emergence of that force, in fact, comes from the fact that we neglect the fluctuation of the number of photons. So basically, at low number of photons, it should disappear, and it could be interesting to study that emergence. And it would also be nice to extend this, the method we developed to optomechanical setups, where adding an oscillator, we should be able to find a fluctuation theorem relating the mechanical oscillations of that oscillator to that of the dressed atoms fluctuations. And with this, I thank you for your attention.
Okay, Dominique.
Thank you for a nice talk. I was wondering, there was a lot of assumptions about starting in a product state. Is this a crucial assumption, and does it also mean that if you don't have this assumption, then the master equation doesn't satisfy the second thermodynamic law?
So by starting in the coherent states, you mean?
No, just starting in a product state. Let's say
I mean, what is really important is this, so this one is important to justify that you even have a quantum map to begin with. Because, okay, so yes, your question is it important to start from factorized states?
Yes.
So yes, it is important because we're using Krauss operators and quantum maps, which make sense if you can basically perform the Born approximation.
Mm-hmm. So if you don't start in product state, then you cannot guarantee that the second law is satisfied.
And for the second law, yes, the second law, at least in the way we derive it, is to assume that you start from a product state.
Okay, thank you.
So, yeah.
Okay, one last question from Matthias.
I have a kind of follow-up question on this, because when you do the derivation, for example, of your fluctuation theorem, you insist quite strongly on the fact that you need this product structure, but in your fluctuation theorem, as far as I remember, you suppose that the atom and the bath are also in a thermal state, or let's say an equilibrium state, right?
Yes, so this is specific to the fluctuation theorem. You don't need that. For the fluctuation theorem, indeed, you need to start from equilibrium states, but you do not need this for the master equation.
And so, maybe to follow up on that, so could you, in principle, make a variation where you do not start from an equilibrium state, but from a non-equilibrium steady state or something like this?
You could, I mean, in fact, for the laser, I assume that I start from a coherent state, so this is a very far from equilibrium state. So, yes, you could play around with those concepts, and depending on what you need to do.
All right, maybe we will ask Ariane to stay if there's any other questions, and otherwise, thanks to Ariane for the wonderful talk.